So today we are going to look at 2's complement representation for numbers. So when numbers are represented in computer systems, specifically signed numbers, which can be either positive or negative integers, okay, signed integers. So to represent signed integers, we usually use 2's complement system. Now what is this system? So in this system, suppose we are given n bits to represent a decimal number using bits. Using these n bits, we want to represent a decimal number. So in this system of 2's complement, we use the first bit for, so these are our n bits. In this system, we use the first bit to represent the sign of the number, positive or negative. If this first bit, the leftmost bit is 0, then the number is positive. If this leftmost bit is 1, then the number is negative. That is pretty simple. So, for example, suppose n equals to 4 for our example. So here we can say whatever this number represents is a positive number. Pretty clear. Now suppose this, we can be sure that this is also a positive number. Now what about this? Don't think about the value that it represents right now, just think about the sign. The first bit, the leftmost bit is 1, so it represents negative number. Okay, now let's look at the values, the other n minus 1 bits. In this case it would be the other 3 bits, represents or used to figure out the value of this whatever this binary represents. Okay, so for the positive numbers, it is just same as taking these bits and converting it into the decimal equivalents. So for example, this represents 2, this represents 1, this represents plus 3, okay, this was plus 2, plus 1, like that. For example, this would represent plus 5. But the case is not same for negative numbers. For negative numbers, it's a little bit different. So I will show you how. Now look at this. For the positive numbers, it is pretty clear that this represents 0, this represents 1, this represents 2, and so on. This represents 4, yeah, this represents 3, and so on. Okay, this represents plus 7. So this was for the positive numbers. So whatever is on that side of the line represents positive number. These have the first bit as 0, but the case is different for the negative numbers. This does not represent minus 7. Instead, here we go like this: 0, this represents minus 1, this represents minus 2, this represents minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. Okay, so that's how 2's complement system represents these numbers. So basically we go from 0, 0, 0, 0 to 1, 1, 1, 1 like this, but after plus 7 it immediately goes to minus 8. Or you can think like going from this direction to this direction in a negative manner, minus 1, minus 1, minus 1, minus 1, all the way till minus 8. So you can think like going like this from plus 7 to minus 8. Now if you divide these two parts here, Here we have 8 numbers which start from 0. Here we have 8 numbers which start from 1. Here it starts from -1 to -8. Here it starts from 0 to +7. So the range is -8 to +7, and we have got 16 numbers. So if we have n bits, it's easy to see that we will represent to the power n numbers whose range would be -2 to the power n minus 1. Why -1? Because we have 3 bits to represent this value. 2 to the power n minus 1 minus 1. Now here understand this. So for the positive numbers, since we are also using 0 to represent 0 itself, that's why here we will need to do a -1 here. We can go only till 7. After that this bit becomes 1. We are starting the count from 0 when we start from 0. That's why we can represent till 2 to the power n minus 1 minus 1. So 8 minus 1 till 7. Okay? Because we started from 0. Here we started from -1 itself. There is no such thing as -0. Okay? So this is the range. And these are the number of different decimal numbers we are able to represent, which is the maximum possible for n bits. You can only represent to the power n amount of numbers, different numbers using n bits, because that's how many different combinations we can have for n bits. Now let's look at negative numbers for a while. The negative numbers value is little bit different. So if you want to convert this negative number into its decimal equivalent, so for positive numbers that is quite obvious. You just convert this part, you get the 2. But for negative number, it's not so obvious immediately. So let's look at how we can convert a given 2's complement binary into its equivalent negative number that it represents. Okay, so the key observation here is that if you flip these bits, or if you flip all these bits, then you will get this. Can you see that? If you flip all these bits, you will get this. So if you flip all the bits of +7, you get -8. Now observe this. This was +6, this was +5. If you flip all the bits of +6, you will get -7. Bits of the -7 number. Can you see that? 0 becomes 1. 1 1 becomes 0 0. 0 becomes 1. So these two connect like this. Similarly, these connect like this. These connect like this. And the pattern continues all the way till here. If you flip all the bits of this, you get this. Okay. So the thing is, if you flip the bits of 0, you are getting -1. If you flip the bits of 2, you are getting -3. You flip, you will get 1 here, 0 here, 1 1. So 1 1 0 1. 1 1 0 1 is -3. If you flip the bits of 2, you get -3. Is it clear? 1 1 0 1. 1 1 0 1. So if you flip the bits of +x, where x is some decimal, if you flip its bits, you will get negative representation of x plus 1. For example, if you flip the bits of 0, x is 0, okay, you will get 0 plus 1, 1, -1. Simple. So that's how we can find the equivalent. If you want to find out the representation of, let's say, -6, okay, so you want -6 here, okay, you want -6 here. If you want -6 here, what you would want here? 5, right? 5. If you put x equals to 5, 5 plus 1, 6, -6. So what's the representation of 5 plus 5? It is this. Just flip its bits. You get this. And let's check now. -6. -6. So this works. Okay. Now, if you are given a 2's complement binary, let's say this, we don't know what this is. How will you find which negative number it represents? Well, you know this, right? So from plus to negative, from plus to negative, how we went? If we flip its bits, it gives us a negative number which has a magnitude +1. If you flip the bits of 0, it gives you -1, right? So we need to figure out which number, which positive number would give me this magnitude. Now let's say you are given this number. We don't know what this number is, okay? But we know this is negative number, and we want to find its magnitude, its value. So how will we find its value? So just flip its bits. If you flip its bits, you get 0, 1, 0, 0, 2. If you flip its bits, it gives you 2 plus 2. But we know that plus 2 matches 2. Plus 2 matches 2, -3. So this means this is representing -3. I hope this concept of convergence is clear. Okay. Now there is one more little trick that you can use. So take 2 to the power n minus 1. Here it is 2 to the power 3. That is 8. Now if you want to find the binary of, let's say, -3, you can subtract 8 minus 3. Okay. If you subtract 8 minus 3, it will give you 5. So you can see this is the binary of 5. So this way is also useful in converting it quickly. Now why does it work? It works because of these decreasing numbers. Here it is 7, here it is 6, 5, okay, and this is representing -1. So 8 minus 7, 1, 8 minus 6, 2, 8 minus 5, 3. So like that also you can convert. So I hope this conversion is clear. Now we will look at the overflow condition in this system. Now what do I mean when I say overflow? Now this 2's complement system works pretty well for additions. For example, if you add +2 and -2, so what will be the representation of -2? You would want to flip the bits of +1. Okay, so just flip the bits of +1. This would be -2. Let's just confirm once. Yes, this is -2. Okay, so if you add these two, +2, -2, obviously you will get 0, and it works here. 0, you add these two, 0, carry 0. Okay, and you discard the last carry that you get, so this is 0. But sometimes since we know that these 2's complement can only represent the numbers from minus 2 to the power n minus 1 to minus 2 to the power plus 2 to the power n minus 1 minus 1. If the sum exceeds this or this, if it goes less than this or more than this, that condition is called overflow. But before that, let's look at why these additions work so perfectly. To see why these additions work so perfectly in this representation, you need to start looking at these bits as counter. Okay, so if you start here minus 8, you add 1, the counter becomes this, 1 is added. So if you can just keep adding any number. So if you add plus 2 here, the counter would jump here and it would become 4 here. Okay, so minus plus, so you here if we add, it goes in this direction, right, which is correct direction. So if you add 3 here, this 2 become 5s, and we know that minus 6 plus 3 is minus 3, so in this direction, so it works correctly. Okay, and after minus 1, if you add 1 here, the counter resets to 0, so 0. That's why the arithmetic works out very well. Coming back to our overflow condition. Okay, so there is a very nice way to check how to check the overflow. There is very nice way to check the overflow condition. Okay, so we can have 3 cases here: plus plus, minus minus, plus minus. What do I mean by this? Is that we are adding 2 numbers, one of them is positive, another one is also positive, one of them is negative, another one is also negative, or they have different signs. So in all these 3 cases, we are going to see that using a single condition, all 3 these cases can be resolved, and we can check for overflow very efficiently. So we just need one condition to check. Okay, so let's look at plus plus for first of all. So the sign bit would be just 0. Here we will have some bits. The sign bits of both the numbers would be 0 and 0 because both are positive numbers. So here these two will be producing some carry here. Now when will overflow happen? When overflow? So let's look at when will overflow happen. First of all, so whatever the carry is produced by these two, or this summing up these two numbers, whatever the carry produced is, the carry out in this case will always be 0. If 1 is carry, here we will just write 1 in the sum, but still the carry is 0. 0 plus 0 is 0, 0 plus 1 is 1, but the carry is 0. Okay, so the carry out in the case of plus plus will always be 0. Let's look at the carry in. So if we are having a carry in of 1, we sum these two numbers up and we get a carry of 1 here. That means overflow. Why? Because both of these numbers are positive. Okay, and we are summing these two up so that it produces a 1 here. That means the sum is a number greater than this number. It cannot be represented using these many bits. Okay, if it was represented using these many bits, there wouldn't have been a carry. Okay, so whatever the sum of these two is, it produces a carry. That means it cannot be represented using these many bits, hence it is greater than this. Okay, because these bits can only represent from 0 to 2 to the power n minus 1, and since the sum produced a carry, the sum is greater than this, hence hence overflow. So when the carry is 1, we have overflow in this case. And if the carry was 0, that means the sum was within this range. Okay, sum was within this range, hence no overflow. So this was the case for the plus and plus. That means both the numbers were positive and positive. Now let's look at the case where one is positive and another one is negative. Okay. Now, in fact, we don't have to look at this case. You know why? You know why? Because this can never result in an overflow. Why is that? Just look at the number line. Here we have 0. Here we have plus to the power n minus 1. Here we had -1, I'm sorry. Okay, and here we have minus 2 to the power n minus 1. Now, one number is negative, one number is positive. Whichever has greater magnitude, we just need to cut that much amount of from the other magnitude. Suppose this magnitude is greater than this magnitude, then the resulting number would lie somewhere here. And if the magnitude of the negative number was greater, the resulting number would lie somewhere here, but it can never overflow. So this case is not nothing to worry about. So let's look at what the carry in and carry out would be, so that we can form this single condition which we can use to check, always check for the overflow. So in this case, the carry out can be 0 or 1. So if the carry in is 0, the carry out would be 0. So if the carry in is 0, the carry out will definitely be 0. So this was carry in, this was carry out. If the carry in from these numbers, adding up these numbers, is 1, the carry in 1 plus 1 would be 0, but there would be a carry, so the carry out would be 1. So you can see both will be the same. So carry in and carry out will always be same in this case. Okay. Now let's look at the third case, which is negative and negative. So here both the sign bits would be 1 and these other n minus 1 bits would produce some result. Okay, so here also carry in, carry out. Okay, so if the carry in, so these two are both negative numbers, right? So what happens when we had two negative numbers? We had a negative number, right? So the result sign bit, the sign bit of the result should be 1. But if the sign bit of the result is not 1, that means we have an overflow, right? Same as that case for the positive numbers, right? So when we had extra carry, the result would have 1. That means we have an overflow. So if we add these two numbers, we add these two negative numbers, and we are getting 0 here, we are getting 1 here, that would result in a 1 here. If we are getting a 0 here, that would result in a 0 here. And if we are having a 0 here, that means negative makes a positive, which is not possible. That means we have overflow. We are out of bounds. We cannot represent using this system that number. That is undefined. Okay. So what we are saying, the carry in is 0, then this would become 0. Okay, which is causing the overflow. So this causes overflow, and the carry out is 1 in this case. Okay, 1 plus 1, 0, 1 carry out. If the carry in is 1, if the carry in is 1, we have a 1 here, 1 plus 1 plus 1, and we also have a carry here, which is 1. But this is not a condition for overflow. So this was overflow and this was not overflow. Okay, not overflow. Now I will show you the interesting pattern that is there in all these three cases. So the pattern is that one condition, that is whenever carry out is equals to carry in, whenever the carry out is equals to carry in, there is no overflow. But when the carry out is not equals to carry in, there is overflow. So let's look at the first case. We had carry out as 0 always, and when it was 0 there was no overflow. So carry out equals to carry in, no overflow. Carry out not equals to carry in, overflow. In this case both were always equal, so in this case there wouldn't be any overflow, but carry in and carry out are always equal, so this condition still is good. Okay, and in this case when carry in and carry out are not equal, we have overflow, and when carry in and carry out are equal, we don't have overflow. Okay, so just to check if it results in an overflow or not, calculate the carry out and calculate the carry in from the sum of these two. Check if they are equal. If they are equal, then there is no overflow. If they are not equal, there is overflow. Thank you for watching.